Welcome everyone to the fourth lecture, and this in this lecture we will see what are these special kind of boundary value problems, and we will start off with the plane strain boundary value problems. Okay, and we'll see how the formulation is, how the boundary conditions get simplified, how the domain equations also get simplified, and what are the ways by which we can solve it. Okay, so let us go ahead. And before we begin, let us all have a common understanding uh, so that we have a sense of things, what are the assumptions that we make. Let us begin. Objects in general are four-dimensional. Okay, you pick a chair, football, blackboard, human body, anything. All these objects are four-dimensional. Just that the fourth dimension is time. Okay, the volume of our body or the shape of our object or the shape of the chair, all of them are not only function of position vector but also in time. For example, at this moment the chair is at the chair or a table is at a particular position at t is equals to 1 second. So and so is the domain of the object, and let's say in the next second I have moved the object, which means the domain also has shifted from one position to the other position, right? And maybe I have maybe bent the chair also. So I can do various operations. So objects in general are not only function of position, but also function of time. So they have four dimensions. And in this course of elasticity, we have already said we will look at problems where there is no dependence on time. It's not, I'm not going to analyze me sitting on a chair or me walking on a floor. I'm going to analyze the problem of me already sitting on a chair. I'm sitting on a chair and I want to analyze the deformation of the chair. Okay, an object is placed on the table. I want to analyze the deformation of the object. I'm not worried about the moment when I start to apply the load to when it stabilizes. We are looking at static problems basically. And all objects are three-dimensional. There's no dependence on time, so objects become three-dimensional for us. However, you will realize that some engineering structures, such as rail as in the rails used on a Indian railway trains, okay, dams which hold water, then carpets, walls, the paper which we write, the floor, what else? The window glass planes. What next? What else can we say? The false ceiling. Okay. All these objects can be analyzed in two dimensions. Okay. And although physically speaking, if you look at a paper, it has certain thickness. It may be 20 micron, 30 micron, 100 micron. But for most engineering analysis, it is sufficient if we analyze things inside in the plane of the paper instead of analyzing the entire structure. If you look at the railway rail, the rail on which the train moves, that rail is very long. Okay. And if I cut any cross section of the rail, it will basically be the same shape, same material, and the loading is also more or less same. More or less. Except, see, you know that a rail is connected to the sleepers by a bunch of rivets, spring kind of rivets. Except in those regions, otherwise the loading, the deformation, everything will be the same. Similarly with a dam, there is water on one side, there is no water on the other side. You can walk along the length of the dam and you will realize at every cross section of the dam, if you see your left hand side as well as the right hand side, on the top side, on the bottom side of the dam, you will see that the boundary conditions are the same, whether you are at this end of the dam or anywhere in the middle or towards the end of the dam. Okay, so in these kinds of cases, it is sufficient if you analyze the plane of the object. Okay, things like paper-like structures which are very thin and long structures, it is enough if you analyze their cross sections. And again, there are certain differences, like you need to analyze a paper differently. Okay, whereas in the paper, 2 dimensions are long as compared to a third dimension. Whereas in case of rails and dams, 1 dimension is very long compared to the other 2 dimensions. Okay, and these kinds of analysis can be classified into plane strain, plane stress, and anti-plane shear problems. And we will look at in the next few lectures, we will try to analyze these problems using stress formulation as well as displacement formulation. Clear? Okay, so let us continue. So this, I thought this sort of an overview or an understanding, or we all should be on the same level as to when it comes to thinking about the dimensions as well as approximations of 3 dimensions to 2 dimensions. So this is a plan. As I said, we will analyze plane strain and plane stress problems using stress formulation. Then once we formulate, we will formulate the general solutions. We will, when I say formulate, I mean the correct term should be identify or determine the general solutions for Airy stress function. And the solution, we will do it in various styles. Depending on the problem, we have a tendency as engineers to choose a whether a Cartesian coordinate system or cylindrical coordinate system or spherical or even polar coordinate system. So we will identify that solution in various coordinate systems, and in each coordinate system different kinds of techniques, so that by the end of this course you are like a well-oiled mechanical engineer. You should be able to solve many engineering structures, and we'll solve some classical problems, okay, such Fleming's problem, as well as some very fundamental problems such as bending of cantilever beam. And we will solve some problems using displacement potentials as well. Okay, so we will analyze plane stress problems, plane strain problems, and in both these kinds we will solve using stress formulation as well as strain formulation. Okay, so you will solve problems which cover this entire spectrum. Okay, and in displacement potentials also there are some classical problems such as Kelvin problem, which is nothing but you have an infinite object and you have a point load acting on it. Okay, and we will also solve at least one problem we will solve using displacement formulation and stress formulation, and the same problems we will also try solving it without using the Airy stress function. Remember, I was telling you in the previous lecture and the lecture before, you don't have to use the potentials or the Airy stress functions or the Helmholtz potentials. Once you formulate your stress or displacement based formulation, you can solve the problem without resorting to the potentials also. Is that in some cases it becomes tedious. Okay. So this is the plan for the next set of lectures. Okay, so let's begin. So consider these examples. One is a dam. On one side, you can see that there is water, and the other side is simply atmosphere, and above water is also atmosphere. Okay. There's a tunnel. The tunnel is extending in and out of the screen of the computer. So is the gravity dam. It is extending in and out. And next is the wall. What we are seeing is the cross section. Basically, all we are seeing in these 4 pictures are the cross sections, except the optical cable, of course, where you have. Has anybody seen optical cable? You should do a Google image. Most likely you have seen it, just that you perhaps didn't recognize it as optical cable. Now that we are talking about optical cable, I would recommend everybody to look at optical cables in ocean. How are we able to talk to a person in Australia? Or how are we able to view a website which is made in Australia? There are cables lying in the ocean. So you'll get some very nice images if you do some such. So these are these long cables extending for thousands of kilometers. Okay. So in all these 4 examples, dam, tunnel, wall, cable, all of these objects are very long compared to the cross-sectional dimensions of length, of breadth and height. The length is very long as compared to them, which also means if I section, for example, this cable at this length, and so on, the behavior about every section will more or less be the same. We have this wall extending towards and outside us. So if I chop the wall, I know not really, but fictionally, if I bifurcate the wall perpendicular to its plane, you will see that there is no difference in terms of load and as well as the deformation. Primary example, the easiest example is the cable. Imagine this fellow is in an ocean and it is long. Every section, at every cross section, the loading is the same. Okay, we are not looking at examples where I have a cable and here there is one kind of load, here there is another kind of load, F1, F2, then there's a displacement, then there's another kind of force. No, I am not talking about this kind of force. This type of loading on a long dam or wall or tunnel, or even for that matter an optical cable. We are looking at those cases, for example, dam, tunnel, wall and cable, where the loading as you go along the length remains the same. So if on a cross section, your loading is a function of R, where R is in 2 dimensions now, xi plus yj. Your loading as a function of R only, and it is constant as you go along the length. Okay, we are analyzing those kinds of problems. As you're walking along the dam, you will see that on your left hand side there is water, on the right hand side there is no water. You walk 2 more meters along the dam, you will see the same boundary conditions, and so on. Same with the tunnel. When you're entering the tunnel versus when you're in the middle of the tunnel at various positions, the loading on the tunnel is the same. Okay, we are not changing the load. In that case, you cannot say make a 3-dimensional problem, convert a 3-dimensional problem into a 2-dimensional problem. Okay, so we are looking at structures, one of whose length is very long compared to the other 2 dimensions, and the loading in a cross section is the same at every length of the structure. Let me repeat, the loading in a cross section is the same at every length of the cross section of the structure. Okay, these are the observations, the same thing which I've been telling again and again. The dimension is very long. Everything is the same along the length, as in they are independent of z. It's a constant function with respect to z. Z is the axis. So when I say z, so this is y and this is x. So which means z is the guy which is outside. Okay, body forces, traction, displacement, everything are independent of z. And deformation is same in every parallel cross section. Okay, these are our observations. Okay, I suggest that you rewind the video and listen to these observations again, or start slide number 4 again. Very important. Okay, it's not like I have a cable and I have different kind of loads at different cross sections. You're not analyzing those problems. That's more complicated. We're trying to analyze common engineering structures which have where the geometry is long, the cross section is the same. You know, I'm not analyzing the case where the cross section of the gravity of the dam is changing along its length. That's a different problem. Where we are not analyzing even an optical cable where the diameter is reducing. No, we are not even solving this. We want the diameter to be constant, and the loading in every cross section is the same. Okay, these problems can be solved as what is called as plane strain problem. Okay, so it is enough if I analyze one cross section of the problem, one cross section of the structure. So the structure I have shown here, this is the cross section. And how does the structure look like? Extend this structure in and out of the computer screen. So you get a long bean shaped structure. And these are the axis convention which I am going to choose. Okay. And in these cases, there is, since the boundary conditions are the same along Z, okay, the loading is the same at every point of Z, effectively there is no strain. What are we saying so far? We are saying all the boundary conditions, whichever they are, SU or ST, they are independent of Z. Dou U by dou Z of these conditions is 0, which includes dou W by dou Z is also 0. This basically means that epsilon ZZ is 0. So in all plane strain problems, this is how your form looks like. And we have been saying our strain is a function of displacement, right? And now you will see that in that displacement, there is no longer Z. Z hai nahi. It is simply every component, all the 4 components, you have it as a function of X and Y. Although I've written epsilon XY and epsilon YZ, by definition they are the same. And so this is the long structure, and the cross section is the same everywhere. As I mentioned, the diameter or whatever is the cross section should not change. Let's say this is the normal. These are the general normals, in three-dimensional body force, and this is the Cauchy stress, definition of Cauchy stress. Okay, if I look at the cross section, remember we are analyzing the cross section. In the cross section, there is only the normal also lies in the X and Y planes, which means the Z component of the normal is 0. Right? Once this happens, I'm simply writing this Cauchy stress in a more matrix kind of form. Okay, these are the general forms of normal vector and body force, and this is the definition of Cauchy stress. And we said it is enough if I analyze the plane, cross-sectional plane of the object. And once I take the cross-sectional plane, my NZ, the Z component of the normal, turns out to be 0. Right? So let's see how this equation simplifies as. So this is what you get. So your traction will basically look like this. So let's see what this mean. Of course, not just Tx and Ty, every component is independent of Z. That is why we are able to do a plane approximation. The entire problem, the geometry has been converted to a 2-dimensional thing. So everything is independent of Z. Again, we are worried about the same cross section. 3-dimensional problem we have converted to 2-dimensional, and and that cross section is what we are interested in, and that's why we are analyzing it. So everything is independent, so you might as well set it to 0. The traction, and you already know the NZ is also 0. Okay, in the plane, I'm doing things in this plane. I'm not worried about the end faces. We are looking at a long optical cable or a long dam. The front face and the back face is not what we are concerned about. That's not what we are analyzing. We are analyzing some section in the middle. We are not analyzing a very short dam, a long enough dam. So any cross section, any intermediate cross section. Okay. So what are the boundary conditions? The displacement boundary condition, as we have derived in the previous slide, the Z component of displacement is 0. Right? And that is when it became a plane strain problem. And the cross sections are same everywhere. I mean, something which I'm rewriting and re-saying the same thing again. And the remaining 2 displacements, U and V, in general, what you had was U is a function of R, which means your small u was a function of R, small v was a function of R, and small w was a function of R. Right? This is a scalar quantity. Now, all we are saying that u is not just a function, I'm making it much more simpler. It is a function of x and y alone. I hat plus v times x comma y j hat. Okay, w is anyway 0 and R doesn't have z component. See, what was a very, when we write it in an expanded form, even this equation also can look very complicated because you have u, v, w, and R is a function of x, y, z. We have removed z, we have removed w. So we are sort of slowly reducing variables. Now, boundary conditions on the planar surface, and z is equal to the ends. Okay. Previously, we were not worried about the ends until here. We were only looking at some random cross section. Now, at the ends, what is it that we were saying? The front face and the back face. At the front face, the normal is +1, and at the back face, it is at -1. So in such a case, the traction on either of the ends, the x and y tractions on either of the ends will turn out to be 0. Okay. You do the matrix multiplication and you would get this particular entity. Clear? And y is sigma is xz0. If you go to the previous slide, we said u is a function of x and y, v is a function of x and y. Hence, if you have xz, what is xz? Dou w by dou x plus dou u by dou z. W is anyway 0, so this term goes off. U is only a function of x and y, so this term is also 0, right? So epsilon xz is 0. That is how epsilon xz is 0, and similarly epsilon yz is also 0. Okay. So maybe when you write your notes, maybe before itself you may want to say this. Something which I said, but just that I did not write it. Okay. So epsilon xz and epsilon yz, both of them are 0. And hence, where are we? And hence your sigma xz and sigma yz are also zeros. Is this clear? So now that we did all these simplifications, let us try to put them together once again. Okay. We have said W is 0 because of the way loading and all are there, and the deformations are independent of Z. So that is why we have only that is U and V components, and that too they are functions of X and Y alone, which are the coordinates of the cross section, which are the variables in the cross section. So we have 3 strain equations and the remaining strains are 0. This much everybody has to be clear now. But this was 0. By the way, all these were 0 of this. If you want, I can redo it once again. Epsilon yz, or previously we said xz. So epsilon yz is dou v by dou z plus, of course, is a half dou w by dou y. W is anyway 0, so this first term goes off. V is only a function of x and z, so this term also goes off. So that's why your epsilon yz is 0, and so is epsilon xz. Why is epsilon zz 0 is something which you know, because W is 0. Okay, so you have 3 strain equations. You have 2 displacements. So you have 2 displacements, 3 equations here. And how do the constitutive relations look like? I have used the initial notation. This is the generic form of the constitutive relation, which you guys know. Right? And I can write it in forward and inverse form. Here I have written it in lambda and mu, which are the lemma parameters. What is E? It's the first time I'm introducing E. So I'm going ahead and writing this as E is nothing but elastic modulus. Nu is Poisson or Poisson's ratio. You can call it either way. Okay. So out of these 4 variables, lambda, mu, and epsilon nu, only 2 are independent, the other 2 are dependent. And these are the forward and inverse relations. How do these simplify? Epsilon xx is this guy. Right? I'm directly using this inverse relation here. Right? And how does this simplify? It simplifies this way. There's not much of a simplification you are doing. I'm just rearranging, grouping the sigma xx terms. Okay. Epsilon yy and epsilon zz. Similarly, there is not much simplification there. I'm directly following the same simplification what I did for here. However, you know epsilon zz is 0 from here, right? Epsilon zz, this fellow is 0. What does this imply? That's what I'm writing. Epsilon zz is 0, which means your sigma zz is, you know that all I'm doing is Until here, I am using the stress strain relations, right? And these are the simplifications I got. And now I know epsilon zz is 0. So I'm equating this to 0, which means you will get sigma zz is equals to nu times sigma xx plus sigma yy. So although you may not have epsilon 0, 0, you can still have a stress component in that normal stress component in that direction z. You have epsilon xy, which is non-zero quantity, and the other two stress components are 0 because epsilon yz was 0, so was epsilon xz, right? So you have, in the shear components, you have only one shear, which is in plane shear, and you have the normal z component, and you have sigma xx and sigma yy. Those are there anyway, which we will see, right? And what is sigma xx and sigma yy? These are direct relations using the previous forward relations. Now you know that these components are 0 and the normal component can be evaluated once you know these two in plane normal components, right? So people put it in a more compact form, which is in metric style this way. So you have in the plane, you have two normal components and one shear component, right? And those you can write it in terms of the components of strain which are relevant to the plane. And what is this P? This P is this particular factor. And it's not done. We have this equation. Okay. You still have a sigma zz component. Okay. So this is the most common form, which when people say, when you look for any literature on plane strain, this is the general form which people write it in. Of course, you can write this expression P in terms of lambda and mu also. Okay. I think you guys should go ahead and write it. Replace E in terms of lambda and mu, and nu also in terms of lambda and mu. So this is the compact form of plane strain problem. So originally your constitutive relations were 6. Now because these two guys were out, you have now how many? 3 here and 1 here. You have 4 constitutive relations. 3 stress strain relations and 2 displacements. So how many? 2 displacements. We will count it, don't worry. So you have, and what is remaining? The equilibrium equation. Okay, sigma zz is 0, sigma xz is 0, sigma xz and sigma yz are 0. So you are left with these 2 equations alone. Strain compatibility. How many strain compatibility equations did we have? We had 6 strain compatibility equations, right? I'm going to take the first equation. Can I simplify it any further? I know epsilon yz is 0, epsilon zz is 0, epsilon xz is 0. None of them are featuring here. So this equation doesn't get simplified. A quick homework for you is, just so that you're following the lectures, what happens to the remaining equations of strain compatibility? I'm going to use the first equation, but I would like you to check what is happening to the remaining 5 equations of compatibility. Okay, I've already declared that, no, it's not that I declared. You all know that this is the case, right? Xz and Yz are 0. So you check how are those remaining 6 equations? Why am I not using them? I will leave that as a homework. Maybe that's a good question for a quiz. I do have a habit, whatever problems I declare this way, I might give them in the quiz or I might give them in the exam. So you may want to check what is happening to the remaining equations. Okay. So I'm saying eliminating strains in the last 7 equations. What are these 7 equations? We had 3 strain displacement relations, right? This is the first, second, and third. We had 3 strain displacement relations. How many constitutive relations we had? 4 constitutive relations. So far our equations are 7, right? And if I remove, and then I have the 2 equilibrium equations. So all I am going to do is do what we did when we derived the stress formulation and ended up the Beltrami-Michel equations. What did we do there? We substituted for the strain in terms of stresses, right? So we already know from the slide number 7, what are the stresses in terms of, what are the strains in terms of the stresses. And we already have a compact form also, right? You can, now I have written it this way. So you can as well have epsilon xx, epsilon yy, or maybe I should write it here. You can identify epsilon xx, epsilon yy, epsilon xy in terms of a matrix which is multiplied with sigma xx, sigma yy, and sigma xy. Okay, so you know your inverse. This is a compact form, so you can always invert it and find the inverse. So you do the same thing. Okay, that's what I said. Eliminate the 3 strains. And this is what I'm doing step by step. Okay, like I said, like I declared in the very first introductory lecture, we will do the details wherever it is required. I'm eliminating the strains and substituting them in terms of the stresses. And now I'm defining what is called as an Airy stress function. Okay. In fact, before you do that, you must realize what is sigma zz. Sigma zz was nu times sigma xx plus sigma yy. So you substitute for sigma zz in terms of sigma xx and sigma yy. So you will end up with a function which is in terms of sigma xx, sigma yy, sigma xy. Okay. You will end up with a particular function once you eliminate this. And then I'm going to define the function such that this is also called as potential, stress potential phi, because of the following reason given in this last line. I'm going to define a function such that when I take its second derivative with respect to y, I end up with sigma xx. And likewise, if I differentiate with both of the in-plane variables x and y, I will get the negative of the shear stress. This is how that great man Airy has defined this function. If you guys are interested in mechanics, you should go ahead, and there are still some unsolved problems in elasticity, by the way. So there are problems which maybe your thesis will help you take up. So this is how this function is defined. Okay, and then you substitute these in this function. Then we end up, you do that algebra. The algebra is not difficult. You eliminate sigma zz in terms of sigma xx and sigma yy and use these definitions. You will end up, or you should end up with this equation. I have done this. I have done this derivation already. So, and this is how, this is where you end up. I am sincerely suggesting you should not skip the steps. You should do from here. You substitute for sigma zz, identify, come to this equation, which is a function of xx, yy, and xy. Then substitute for sigma xx, sigma yy, and sigma zz as given by the Airy stress function. And then you will end up with this particular equation. Okay. And this equation is called as biharmonic equation. Okay. This del power 4 is nothing but del square times del square times del square. What is del square? Dou square x by dou x square, dou square by dou y square times dou square by dou x square plus dou square x by dou y square times this. This is what? A plus b times a plus b. So a square plus b square plus b. So you'll end up with dou power 4 by dou x power 4 plus 2 dou power 4 by dou x square dou y square. Okay. And if you have a phi, you will have a phi here everywhere. That's all. That is why it is called biharmonic. This is the harmonic operator. This is a biharmonic operator. Right? What is this equation called? Poisson equation, right? Sorry, Laplace. If you have a delta function, then you call it Poisson relation. But it's a Laplace equation, right? Twice of, if you do one more Laplace, you get into the, and this is a harmonic equation anyway. Del square, some function, del square psi, let's call it psi. del square psi is 0. This is basically the Laplace equation. You take one more Laplacian of this Laplacian equation, you get the biharmonic equation. All right. So you know its expanded form, you know its compact form. So what is the use of this one equation? I had a text here. What is the use of this one particular equation? Remember when we arrived at Beltrami-Michel equations, equations of compatibility, we had 6 equations in terms of 6 variables, sigma xx to sigma zn. We had 6 variables and 6 equations, and all of them were partial differential equations of second order. They're tedious to solve. Now I have one variable and one equation, which is difficult. 6 equations, 6 partial differential equations and 6 variables, or one equation and one variable. Certainly, with my mathematical ability, and I'm sure with most of your mathematical abilities, it is easier to solve one equation with one variable rather than simultaneously 6 equations and 6 unknowns. Okay, so that is why these potentials or stress functions have been constructed. So what is the use? You solve for phi. How do you solve? There are various ways. That is what we will see from maybe the 3 classes from now, 3 lectures from now. You have one equation, you solve that equation, partial differential equation, with the boundary conditions. How do you get the boundary conditions? Boundary conditions are defined based on the problem. Domain equation does not change. Boundary conditions change from problem to problem, right? And then once you know phi, you evaluate stress. How is stress? Sigma xx is dou square phi by dou y square, and if it is sigma yy, it is dou square phi by dou x square, and if it is sigma xy, it's minus dou square phi by dou x dou y. So this is something which we have defined in the last slide. So you solve for phi using the boundary conditions. Once you know phi, you do these simple calculations based on the definition. Once you know sigma, you evaluate strain. How do you evaluate strain? Inverse constitutive law. Once you know strain, how do you evaluate once you evaluate the, I don't know how to evaluate this guy. Once you know the strain, you should be able to identify the displacement. Okay, so then the question remains for us, how should we solve for this fellow phi? Okay. So I hope this formulation of plane strain problem is clear. We started with structures which are very long. And how long are they? They are so long such that the length dimension is much longer than the length in the cross section. And we also notice in those structures, if the boundary conditions are same at every cross section, very important. It's not enough if you have a long structure. You have a long structure whose cross section is the same everywhere, whose boundary conditions are the same at every cross section. Then such a problem can be converted to a plane strain problem. So you simply analyze, it is sufficient if you analyze the motion or the deformation of one plane of the one cross section of that object. Okay, and we ended up with one governing equation in terms of Airy stress function, right? And how do we solve is what is the only suspense. It is actually not a suspense, it will come in 2 weeks in the 2 lectures after. Okay, so a plane strain problem can be converted to a single partial differential equation. Rather, the Beltrami-Mitchell equations can be converted to, those 6 equations can be converted to one single equation when it is a plane strain problem. This is something which you have to understand very clearly. So in the next lecture, we will try to solve one problem so that we see how, without resorting to any potentials, any big complex formulations. The formulations have been done, we will analyze it. Okay, so please revise this before the next lecture so that from next lecture we can start to solve the problems. Thank you.